This lecture introduces the antiderivatives, indefinite and definite integrations. So what is the definitions of antiderivatives? By the definitions, a function's big F is an antiderivative of small f on an interval I when the derivative of big F equals to the small f for all value of x in the interval I. For example, if you're given the function small f, right, f of x, you want to find the antiderivative functions big F of x. Then you just need to find the functions whose derivative equals to small f of x. So if f of x is equals to x, then big F of x equals to, say, x squared divided by 2, because the derivative of f of x, big F of x, equals to the derivative of x squared over 2. And as you know, that is going to be equals to 2x over 2. It equals to x. So x here is the function's f of x. So we know that by verifying this antiderivative functions, big F of x, by taking the derivative of big F of x, and if it's equals to the original function small f of x, then you know that big F of x equals to x squared over 2 is an antiderivative of small f of x. Okay. Similarly, as you can see that if I have the functions f of x equals to x squared, then the antiderivative functions f of x equals to x cubed over 3. Is that because, right, if you take the derivative of big F of x, that means take d over dx of x cubed over 3, you will get 3x squared over 3. And when you simplify it, it's going to give you x squared. So from these observations, I can try to formulate a formula that helps us find an antiderivative of a polynomial function. So when you have f of x equals to x, then you, in order to find the antiderivative, an antiderivative of small f of x, you raise the power up by 1 and you divide it by the small, the new power, right? So x raised to x squared divided by 2, x squared raised to x cubed divided by 3. So you raise the power up by 1 and you divide it by the new power. All right. How about when you have a function 1 over x, then an antiderivative of 1 over x equals to ln x, right? Because you take the derivative of ln x, you get 1 over x. All right. And you want to have, and in this case, because ln x is always, is only defined when x is positive. So then maybe you want to have a absolute value here, just to make sure that the value x here inside the absolute value is non-negative. All right. Next one, if you have the function cosine of x, then what should be an antiderivative of cosine? So I would say sine and cosine are related. So I would say sine, right? Because if I take the derivative of the sine functions, I would have cosine. Okay. Then the next one is, what is the an antiderivative of e to the x? This is a simple one because it should be just e to the x, because if you take the derivative of this antiderivative, you get e to the x. Okay. Well, last one. If you have a function e to the x times cosine of e to the x, so what is your guess of an antiderivative of this function? As I say, cosine, antiderivative cosine is sine of x, right? And then you have ex here, and you have e to the x out here. That means you can combine them together. It's because the derivative of sine of e to the x using chain rule is going to be equals to e to the x times cosine of e to the x. So in Calculus 2, in the next class, you will learn how to find this antiderivative using a method is called substitution. But in this class, we were just trying to guess, right? What is the antiderivative using our intuitions about the derivative functions. So why are we just finding this one an antiderivative, not the antiderivative? It's because you would have like a family of antiderivatives for a specific function f of x. So the theorem 5.1 says if big F is an antiderivative of f on the interval I, then G is an antiderivative of f on the same interval if and only if G is equals to big F of x plus a constant. What does it mean? That means let's look at this function's f of x equals x. And an antiderivative of f of x that we found is x squared over 2. So let's say this is x squared over 2. It's one antiderivative that we found earlier. What if I raise this functions by 2? I have these functions. So you would have x squared over 2 plus 2, right? What if I raise this functions, lower this function down to -4 here? Then I would have x squared over 2 minus 4. So these three functions is a family of the antiderivatives of the functions f of x equals to x. So using one function f of x equals to x, I have, let's say, one antiderivative functions equals to x squared over 2. And I have another one, right, equals to x squared over 2 plus 2. And I have another one equals to x squared over 2 minus 4. So these three functions are antiderivative functions of f of x because if I find the derivative functions of f prime of x, right, is equals to 2x equals to x, right? And the derivative of the second antiderivative function is the same because the derivative of the constant is 0. Derivative of the constant is 0. So the derivative of the second and the third antiderivatives here is equal to x, which is, that means this here is a kind of a part of a family of antiderivative functions. So again, if you have different constants and you add different constant to a antiderivative function, you have another antiderivative functions of the same functions here. Okay. Now it leads us to the questions of finding the general solutions of differential equations. So what is a differential equation? A differential equation is an equation that involves the derivative functions. Let's say g prime of x equals to x squared. Then you want to find the general functions, general solutions of these equations. General solutions mean you need to find the function g of x such that g prime of x equals to x squared. How can you find g of x? All right. So, and how many particular g of x that you can find? Okay. So again, I have a differential equations, g prime of x equals to x squared. And what is the function g of x that if I take the derivative of the function g of x, I get x squared. So the functions, what do you think? Are we finding the derivative of these functions, or are we finding the antiderivative of these functions? Okay, so in order to find g of x, we need to find g of x. That means finding the antiderivative. An antiderivative of x squared, right? Because once you find the antiderivative of x squared, you take the derivative of it, you will get x squared. So what is an antiderivative of x squared? There's g of x equals to x cubed over 3, because g prime of x equals to x over 3 equals to x squared. So we found g of x equals to x cubed over 3. What does that mean? That means if you have a differential equations, in order to find the general solution g of x, you should find the antiderivative of the functions x squared here. But is the only solutions? No. This is one of the solutions. And keep in mind that we can always add these functions to a constant. Right, in order to find a solution for this differential equations. So you can always add a constant. So that means the g of x function g of x equal to x cubed over 3 plus c is a general solutions to this differential equations. G of x equals to x cubed over 3 plus c is the general solution to the differential equations g prime of x equals to x squared. How many particular g of x you can find? If c is a constant, then we have infinite many solution, infinite many value for c. Thus, we would have infinite many particular functions for g of x. Okay, so if you have a different constant, you would have a different antiderivative. You have a different solutions. And g of x here, again, it's just the general solutions. And we've learned how to find a particular solution for differential equations given an initial value a little later. Okay. So the process of finding the general solutions to the differential equations is called anti-differentiations or indefinite integrations. Right? Process of finding the general solutions. Okay, and it's denoted by the sign, integral sign here. So the general solutions is denoted by, so the y, right, equals to the derivative y equals to integral of f of x dx, and it is equals to the antiderivative functions of f of x plus a constant c. Okay. So the above notation means that big F of x is an antiderivative of small f on an interval. And the expression's integral of fx dx is read as the antiderivative of small f with respect to x. X is the input, and having dx here, the differential dx here, that means x is the input of the functions. Okay. So there's two basic integration rules that you want to keep in mind. First, the antiderivative of the derivative of a function is itself. So if you find the integral of the derivative of the functions big F of x, you get big F of x. Okay. And then if you take the derivative of an antiderivative, you will get F of x out. So the antiderivative and the derivative functions work similarly to how inverse functions, right? If you inverse of a function, you get an x out. Similarly, if you integrate a derivative, you get the original function out. All right, now we can try to find particular solutions to a differential equations given some initial conditions. So you can see that the equation y equals to the integral of fx dx has many solutions, right? And each solution is different from the others by a constant c. So and then this again is equals to big F of x plus c. If you have a different value for c, you will have a different particular solutions. In many applications, real application, you will have some initial values to determine a particular solutions. And before you can find a particular solution, you need to find the general solution. Then you will use the initial value in order to figure the value of c. And once you have the value of c, you can find that particular solutions. Okay. Well, let's look at an example here. So first you want to find the general solution and find the particular solution that satisfies the initial conditions. So this is a differential equation, and this is one initial conditions. Differential equation involves derivative functions, and initial condition involves the original functions, right? The point where the particular function starts. So in order to find f of x, you find the f of x, again, is the antiderivative of this function e to the x. So f of x is an antiderivative of e of x, e to the x, right? So that means f of x equals to e to the x, because the derivative of f of x equals to e to the x. This is how we check our answer, right? In order to find the antiderivative, you find an antiderivative and then you take the derivative of the antiderivative to see if it goes back to the original functions. So we found f of x equals to e to the x. Not yet. So that means the general solutions for this equation is big F of x equals to e to the x plus c, right? Because again, you have many possible solutions for this particular differential equations. But now that you have, using the initial point f1 of 3, you can find c. So use f1 of 3 to find c. By what? By how? By plug 1 into the x and 3 into the y. So 3 equals to e to the 1 plus c. So then c equals to 3 minus e. You just found c, right? E minus e is a constant. That means now you can conclude that the particular solutions is f of x equals to e to the x plus 3 minus e. That's a particular solution. And this is the general solutions. The general solution always have c, and the particular solutions always have a determinant value of c based on the initial value. All right. Now let's look at this, the second example. Again, in order to find f of x, you just find the antiderivative of these functions here. Antiderivative of 2x squared is 2 times x cubed, right, divided by 3. And antiderivative cosine should be sine, because derivative of sine is cosine, and antiderivative e to the x is e to the x. So you can check whether your antiderivative is correct or not. Just find the derivative of big F of x. You have 2 times 3 over 3x squared plus cosine of x minus e to the x, and this should be 2x squared plus cosine of x minus e to the x, right? So just checked. So we know that this is the antiderivative, and then you need to add c to get general solutions. And then the next step, in order to find particular solution, you need to find c. How can you find c? You just need to use the initial value. So find particular solutions, plug 0 into x and 2 into y to find c. 2 equals to 0 squared plus cosine 0 minus e to the 0, 2 equal plus c, 0 cosine 1 minus 1 plus c, so c equals to 2. So it's the initial value. All right, so once you determine the value of c, you just need to plug c into your general solution to find the particular solutions. Let's say f of x equals to 2 over 3 x cubed plus sine of x minus e to the x plus 2. All right. Next example. So this example involves the second derivative of a function, right? It's also a differential equations, but it has second derivative functions involved. And then it has 2 initial value, one for the first derivative and one for the original function. So let's try to find it. Again, we just need to, you have the second derivative, you get to the first derivative. In order to find the first derivative, we just find the antiderivative of the second derivative. So the antiderivative of cosine is sine, because the derivative of sine is cosine, right? Plus c. And then now you use the first initial value to find the c. Okay. By plugging it in, you have 0. So 1 equals to sine 0 plus c. So then c equals to, this is 0, c equals to 1. So the first derivative is sine of x plus 1. Okay. Now the goal that you want to find the original function f of x. That means you want to find the antiderivative of sine of x plus 1. Antiderivative of sine of x should be negative cosine, because the derivative of cosine is negative sine, so negative of cosine should be sine plus x, right, plus c, because the derivative of x is 1. And now you need to find this c using this, the second initial value. Using the second initial value, you will get 2, right, equals to negative cosine of 0 plus c. Negative cosine is 1, negative 1, 2, so that means c equals to 3. So you plug 3 in here to get your particular solution. So the particular solutions is f of x, right? The original functions equals to negative cosine of x plus 3 is your particular solutions to this differential equation.